Hello, everyone. My name is Lionel,
I'm
and
Jared.
this is our presentation on electron spin. This is our topic relating to the course of quantum chemistry, Chem 112. And yeah,
So the electron and what about it? How electrons are usually visualized, as we can see on the right, is that what an electron isn't is it is not a single particle that follows a set path surrounding a nucleus, but what it is that there's a density that surrounds the nucleus where we can most likely find the electron. And as for spin components, the spin component is set as the fourth quantum number m sub s, and it is labeled as either spin up or spin down. Spin up is can be also known as alpha, or spin down can also be known as beta, where m sub s is equal to either plus or minus 1/2, where 1/2 is where north faces up, and minus 1/2 is where north faces down. So what is spin? Spin can be most easily visualized by the Pauli exclusion principle, where each orbital can only hold 2 electrons, and these 2 electrons within the orbital must have opposite spin. So one must have m sub s of plus 1/2, and one must have an m sub s of minus 1/2. There can be singly occupied orbitals where it could either be a spin up or spin down electron, and opposite spins cause the diamagnetic nature of atoms, while the singly occupied orbitals can cause the paramagnetism, where we see, with the images that we see on the right-hand side, we see an example of the Pauli exclusion principle at the top, where one electron is spin up and the other is spin down. And underneath is showing the correct formatting of when you have multiple orbitals. So even with multiple orbitals, you will still have a spin up and spin down in each orbital, no matter what.
so all this information is relative and it's useful, but why does it matter exactly? As we've explored thus far, electrons have a certain magnetic aspect to them. Depending on the direction of their spin, if they're alpha spinning up, they will have a positive 1/2 fourth quantum number value. Whereas if they are spin down, they would have the inverse of a negative 1/2 quantum number value. When these electrons pair with one another, these charges cancel each other out and result in a net charge, which is what we observe with most lone pairs in any bonding atom or molecule. Now, this is very important simply for the fact of how most, if not all, matter in the universe, for that scope, relies on the interaction of subatomic particles. Due to this, should the electron pairs not be paramagnetic and instead be diamagnetic, then we would notice a much more odd and observable form of matter in various states and various fashions that we may not have even properly have ever even considered. But as is nature, that is not the case. Lone pairs have a net charge, which in turn allows for molecules to form. Furthermore, down the line, solids, liquids, gases, all these components of matter to be existing. Furthermore than that, in a much more analytical setting, from electron spin, we can also use a very detailed and viable analysis method known as electron spin resonance, also known as ESR, or often referred to as electron paramagnetic resonance. With this, we're able to observe transitions of spinning states of samples inserted into a cavity as shown in the bottom image, in which we can apply a magnetic field of a certain microwave range to then observe specific properties of said sample. This has obviously expanded into allowing us to have much more detailed understandings into the interactions of subatomic particles and molecules. As such, for our presentation, here are our references, the references of our sources, as well as all our cited images. And in the realm of quantum chemistry, it's always important to remember, you're never really sure if that cat's actually alive or not. Thank you.